Imagine yourself on Mars. For a moment, your spacesuit vanishes. Before you isn't just one threat, but a strange paradox. Your blood is about to boil, but not from heat. Your skin will be covered in frost, but not from the familiar cold. It's a race of 4 deadly forces: vacuum, lack of oxygen, cold, and radiation. Like the 4 horsemen of the apocalypse, they attack simultaneously, and the fastest of them isn't what you'd expect. It's not suffocation, nor is it cold. It's space itself, trying to tear your body apart. This isn't just theory. In 1966, NASA technician Jim LeBlanc accidentally found himself in a vacuum chamber. His last memory before losing consciousness was the sensation of saliva boiling on his tongue. To understand what's happening, we need to look at the numbers. The pressure on Mars is only about 0.6% of Earth's. This value is below the Armstrong limit, the altitude at which pressure drops so low that water boils at normal human body temperature, 37 degrees Celsius, 98.6 degrees. For biology, the surface of Mars is almost a complete vacuum. Such pressure is equivalent to being over 30 kilometers, 100,000 feet above Earth, more than 3.5 times higher than Mount Everest. This survival boundary was defined back in 1947 by U.S. Air Force General Harry Armstrong, a pioneer of aerospace medicine. This leads to a phenomenon called ebullism. Liquids on the body's surface, saliva, tears, moisture in the lungs, instantly boil and evaporate. Water vapor bubbles begin to form under the skin, causing tissues to swell. Blood in the vessels won't boil because the circulatory system maintains its own pressure, but the external effect is horrifying and instantaneous. Imagine abruptly opening a bottle of soda that you've just vigorously shaken. Your body is that bottle. Gases and water dissolved in the tissues instantly turn into foam. Contrary to science fiction myths, the body won't explode. Human skin is surprisingly elastic and capable of withstanding this internal pressure. However, the body will swell almost twofold, especially soft tissues. This process will begin in the very first second, accompanied by complete disorientation and shock, but it's not yet the fatal blow. NASA experiments on animals in the 1960s showed exactly this. Swelling up to double the size, but no rupture. The skin acts not like a fragile balloon, but more like a high-strength elastic suit that can stretch to incredible limits. The first instinct, the most natural one, is to hold your breath, and that will be the quickest and last mistake. There's a golden rule for divers: never hold your breath while ascending. The same thing happens here, only the ascent is instantaneous, from 1 Earth atmosphere almost to 0. The air trapped in your lungs will immediately begin to expand, like a balloon in a vacuum chamber. This will lead to barotrauma. The expanding air will rupture the delicate tissues of the alveoli, the tiny sacs where blood meets oxygen. The only way to survive a few seconds longer is to immediately and completely exhale, but even that won't save you. Air bubbles from your ruptured lungs will enter your bloodstream directly. It's like injecting air straight into a vein, a gas embolism. These bubbles, like plugs, will block the vessels leading to your heart and brain, causing an instant biological short circuit. Once you exhale, the vacuum will literally suck out the remaining air and moisture. Your brain, deprived of oxygen, will begin to shut down. Consciousness will fade in about 10 to 15 seconds. The tragedy of the Soyuz 11 crew in 1971 was a grim confirmation of this fact. Due to cabin depressurization, the cosmonauts died, and post-mortem analysis showed they lost consciousness within those very 15 seconds. This brief interval is called the time of useful consciousness in aerospace medicine. What would a person feel in those moments? The sensation of boiling on the tongue, rapid body swelling, sudden cold on the skin, and a strange metallic taste in the mouth, a neurological reaction to oxygen deprivation. Vision will begin to narrow to a pinpoint, as if the brain is shutting down the periphery to save the core of consciousness. But there's nothing left to save. Darkness descends. The fight for air is lost before it even begins. Consciousness has faded, but the body continues its strange struggle, and now the second horseman takes the stage: cold. But this isn't the cold we know. Temperatures on Mars can drop to minus 125 degrees Celsius, minus 193 derivs. However, it's not like Arctic frigidness. On Earth, cold is primarily transferred through the air, through the movement of its molecules that draw heat from us. But Mars's atmosphere is almost nothing. Its density is only 1% of Earth's. Standing on Mars is like being inside a perfect thermos. dangerous. A vacuum, as is known, is the best insulator. Therefore, the body won't freeze instantly, as if plunged into liquid nitrogen. It will lose heat, but very slowly, mainly through radiation. Much like a cup of hot coffee cools down when left on a table in a windless room. Your body, with a temperature of 37 degrees Celsius, turned to 98.6 degrees, will radiate heat into the icy Martian space. But this process takes minutes, not seconds. You simply won't have time to freeze to death. Paradoxically, the true instantaneous cold will come from the same source as the boiling, from low pressure. Moisture evaporating from the skin, eyes, and mouth will absorb heat at an incredible rate. This phenomenon is called evaporative cooling. It's the same effect that makes us shiver with cold when we step out of a shower into a draft. Only on Mars, this draft is pushed to an absolute unimaginable limit. The evaporation will be so intense that moisture on the surface of the eyes and in the mouth won't just cool, it will instantly freeze, creating the eerie paradox of boiling ice. The skin, especially its moist areas, will immediately be covered in a layer of frost. This will lead to severe frostbite, but the body's core, its internal organs, will still remain warm. Thus, the body becomes an arena of thermodynamic war. From the inside, hot vapor inflates it, like a pressure cooker ready to burst. From the outside, moisture instantly crystallizes into ice, drawing away heat and creating an icy crust, much like freeze drying. It's a war of physical laws, played out on the field of human biology, a war in which life has no chance of victory. But while the body wages this losing war with physics, it is already being permeated by the third, most insidious horseman, radiation. Mars has no global magnetic field, nor does it have a dense atmosphere like Earth's to protect it. Our planet is enveloped in an invisible force field that deflects deadly particles from space. Mars lost its shield billions of years ago when its molten core cooled and solidified. Since then, its surface is an open shooting range with no cover whatsoever. Cosmic bullets, galactic rays from deep space, and streams of particles from our own sun strike it unimpeded. Unlike a vacuum, radiation doesn't kill instantly, but its dose is monstrous. In just a few minutes on the surface, a person would receive a radiation dose considered absolutely lethal on Earth. For comparison, in one day on Mars, an astronaut receives a dose comparable to 6 months aboard the International Space Station. And without a spacesuit, in just a couple of minutes, the body would absorb energy equivalent to hundreds of X-rays taken simultaneously. And that's not even the worst case scenario. If a powerful solar flare occurs, a torrent of protons would bombard the planet. Then a lethal dose would be accumulated not in minutes, but in seconds. This is not theory. In August 1972, between the Apollo 16 and Apollo 17 missions, just such a solar storm occurred. Had astronauts been working on the moon at that moment, they would have perished. Mars, completely unprotected, is even more vulnerable. This invisible enemy strikes at the deepest level. It tears apart DNA strands. Imagine your DNA is the most detailed blueprint by which your body is built and repaired. Radiation is a vandal who breaks into the archive and puts those blueprints through a shredder. Cells lose instructions on how to divide, how to function, how to live. They begin to die off en masse or mutate, initiating a cascade failure of all bodily systems. It's a silent and inexorable disintegration, underscoring a simple truth. Our biology is designed for life only in one cradle, and beyond that cradle, disintegration follows a clear and relentless script. It's a cascading failure, like falling dominoes, where each subsequent one falls faster. The first push is the pressure drop itself. It triggers a chain reaction that sweeps from the lungs to the heart, and from the heart to the brain. Most experts agree that complete cessation of bodily functions will occur within 90 seconds. Gas bubbles born from boiling fluids and ruptured lungs rush with the bloodstream to the heart. And here, biology gives way to pure mechanics. The heart is a pump, perfectly designed to circulate liquid blood, but it is utterly helpless when foam, a mixture of gas and blood, it enters it. Engineers call this cavitation. The pump begins to run dry, its efficiency drops to zero, and the entire system stalls. This is not a disease, not poisoning. It is a mechanical failure of the body's main engine. The brain, even after losing consciousness, is still alive. This supercomputer, consuming 20% of the body's total energy, desperately awaits sustenance, but blood flow is interrupted. It's like pulling the plug from an outlet. The system instantly goes dark. Approximately 1 minute after losing consciousness, irreversible damage occurs. The hard drive is erased forever. The personality itself is erased. So what delivers the final blow? Not the slow cold, not the silent radiation. It's a classic 1-2 knockout delivered by the vacuum. The first punch, hypoxia, sends you down, shutting off consciousness in 15 seconds. And immediately, the second crushing blow follows, circulatory failure due to gas foam in the vessels. It ends the fight, and so the fight is over. The swollen, frost-covered body lies on the red dust. Its subsequent fate is unlike anything on Earth. On our planet, nature's primary scavengers immediately get to work. Billions of microorganisms, insects, and oxygen itself, which oxidizes tissues. On Mars, they are absent. This is the most sterile and cold desert imaginable. Here, the body will not rot. It will be dehydrated and frozen in a process similar to natural mummification. It will be preserved better than Ötzi the Iceman in the Alps or the Inca mummies found on Andean peaks. Low pressure will draw out all moisture, turning ice directly into vapor. This is ideal freeze drying, which will transform the body into a fragile but perfectly preserved relic. However, eternity on Mars does not mean peace. Harsh solar ultraviolet radiation will slowly break down organic molecules. It acts like molecular sandpaper, making tissues brittle, and the thin Martian wind carrying abrasive dust will work like a sandblaster slowly over millennia, eroding what remains, micron by micron. It's a process of disintegration stretched over geological time. Ultimately, the remains will become a silent monument, a testament to how hostile the universe is to the form of life born in Earth's cradle. The irony is that in its decomposition, this body may become the most complex organic artifact on the entire planet, a silent astronaut. The last evidence that life was here and couldn't survive even 2 minutes. These four forces, vacuum, cold, radiation, and airlessness, are not just threats, they are the antithesis of life. Each one is a direct negation of one of the fundamental conditions that made our existence possible: stable pressure, oxygen for breathing, a narrow temperature range, and protection from space. And this thought experiment best illustrates what a spacesuit truly is. It's not just a suit, it's a personal wearable Earth bubble. It's the smallest spacecraft in the world, designed for one person. Hidden within its layers are miles of cooling tubes, a complex life support system, and armor against micrometeorites. It's not clothing, it's a wearable planet. And this technology, this armor, is our only shield. The history of space exploration knows the cost of its failure. A microscopic crack in a helmet, a malfunctioning valve, and all the horror we've described becomes reality in a matter of seconds. Georgy Dobrovolsky, Vladislav Volkov, and Viktor Patsayev, the crew of Soyuz 11, became the only humans to die directly in space. Their death, caused by a coin-sized valve, served as a cruel lesson. In this hostile environment, there are no insignificant details. The price of the slightest mistake is absolute, but studying how quickly and brutally a human dies on Mars is not just morbid curiosity. It's a powerful reminder of how unique and precious our own planet is. Every breath we take without thinking is a luxury almost impossible anywhere else in the universe. This entire terrifying scenario, played out on Mars, occurs under conditions that are normal for space. It is our Earth, with its dense atmosphere and magnetic field, that is the rarest, almost miraculous exception. And understanding this cosmic hostility is the best way to grasp the value of our pale blue dot, our only home.